Hi everybody, welcome back. So today we're going to talk about extragalactic astronomy. This is going to be more of an overview. I mean, you can take entire courses on this subject, and we're just going to get into some of the basics. I'd love to talk in more detail about some of the aspects like galaxy formation and stuff like that, and maybe I will next time I make one of these videos, perhaps next year, on this subject. But for now, we're just going to take an overview of this. But still, it'll be enough. So some motivating questions. How far away are the galaxies? And what do these galaxies tell us about the Milky Way? How did the galaxies form? And what are these things called quasars? We talked about that a little bit back when we discussed black holes, but we're going to have some more to say about it here. What happens when galaxies collide? Do stars collide? And why do nearly all large galaxies have supermassive black holes at their centers? So, about these galaxies. Starting in the 1750s, telescopes had advanced enough that people were able to see some funny shaped cloudy objects in the sky. I mean, during a little bit after that was when the famous Charles Messier started making his catalog of fuzzy things that aren't comets because he wanted to become famous by discovering comets. So I think he did discover a few comets, but they didn't make him famous. It was actually his catalog that made him famous. But the point is, by this point, we had enough resolution in our telescopes to be able to distinguish some features in some of these objects. And some objects in particular that started kind of coming out were these kind of disc-shaped, face-on disc-shaped objects, things like what we now call the whirlpool galaxies, stuff like that. And in fact, it was Immanuel Kant who was a bit interested in this type of stuff, and he hypothesized that each spiral nebula, though it wasn't given that name yet, was in fact a large system of stars just like our own Milky Way galaxy. Now, the name Spiral Nebula, I believe, came from William Parsons, the Earl of Ross, who had this really giant telescope that was often called the Leviathan that he used to observe, and he was actually clearly able to see spiral structure in things like the Whirlpool Galaxy, that is M51, and some of these others as well. Now, there wasn't all that much support for Kant's hypothesis, so really this kind of got swept under the rug for a while. But then our telescopes got better and better until this finally built up in the so-called Great Debate of 1920, 100 years ago, between Harlow Shapley and Heber Curtis at Harvard. There were two main subjects of this debate. One was the size of the Milky Way and our sun's location, and the other was the nature of the spiral nebulae. They both agreed at some point, I guess, during the debate, that really the most important point on this was the nature of the spiral nebulae, the size and shape of the Milky Way and our sun's location. That was more just kind of one of these offshoots in the debate that came up under Harlow Shapley's discussion. But it was two different ideas of how the universe was. One was by Harlow Shapley that the Milky Way is very large, so a diameter of 100,000 parsecs, that is like 326,000 light years if you take that conversion exactly, but here we're talking about order of magnitude. In fact, I think Shapley's order of magnitude would have really converted to closer to about 400,000 light years in diameter, because I think he had it as a little bit over 100,000 parsecs. Shapley had our sun not at the center, he had our sun outside of the center, and Shapley believed that the various spiral nebulae, things like the Great Nebula in Andromeda, M31, the Great Whirlpool Nebula, M51, Bode's Nebula, M81, etc., were actually just things located in the Milky Way. And Heber Curtis believed that the Milky Way was a good bit smaller than Shapley. He figured it was about 10,000 parsecs in diameter. He believed that our sun is at the center, and he believed that the spiral nebulae were island universes similar to the Milky Way, but much farther away. Now, in most of the sources I've come across, it's generally agreed that Harlow Shapley won the debate. Though I will mention I came across a fairly authoritative source quite recently where the audience seems to be under the impression that Heber Curtis had won the debate. Now, Curtis did have to admit that if Adrian von Maenen's observations, he was a Dutch astronomer, of potential rotation in the galaxy M101, what we now call the Pinwheel Galaxy. If those observations were correct, then Shapley's interpretation of the spiral nebulae was probably correct. But that seemed a little bit hard to really confirm. It eventually turned out that von Maenen's observations were incorrect. So here is M101, the Pinwheel Galaxy. Von Maenen had supposedly observed a little bit of rotation in these spiral arms over the time scale of something like decades. And if that was true, that would be a problem, because at least it would be a problem for Shapley's idea that these things were island universes. Because if this is an island universe well outside of our galaxy, if it was showing visible rotation over the time scale of a human lifetime, that would mean that the outer parts of the arms would have to be going faster than the speed of light. And we know that Einstein says you can't do that. So that would be a problem, though it turned out that von Maenen's observations were wrong. Now, the thing itself is actually 25 million light years away. It has a mass of something like 1 trillion suns. It's a bigger spiral galaxy than the Milky Way. Its diameter is something like 180,000 light years. But I should mention, the thing is rotating. We know that it's rotating. We can measure at least a component of its rotation, but that's using the Doppler effect to measure the velocity. When we measure rotation speeds of objects that are really big, like galaxies, we don't look at it one day and then a few years later look at it again and take the distance that it rotated and divide by the time to get the speed. No, we just use the direct Doppler method. We take a spectrum of the galaxy, and based on either the spread in the line widths for the various spectral lines or the difference in the recession velocity or approach velocity, depending on which part of the galaxy you're looking at, astronomers can figure out the actual rotation speed. Now, meanwhile, back to this guy, Edwin Hubble. So, Heber Curtis supported his idea that things like M31 were outside of the Milky Way by noticing novae, new stars in this. And that led to the conclusion that based on the known brightnesses of these novae, which we mentioned in a previous discussion, are the situations where white dwarfs accumulate some matter onto their surfaces, and that matter eventually undergoes some nuclear fusion until all that matter is fused, and then it goes back to being a normal white dwarf again. Well, those things have a relatively well-known brightness, and Heber Curtis noticed some novae in the Andromeda Galaxy and realized that, hey, this is outside of the Milky Way. Well, Shapley countered with his observation of a nova in the Andromeda Galaxy back, or at least not his observation because he was too young, but an observation that had been made of it back in, I believe, the 1880s. And it was very bright, and Shapley used that observation to counter and say, hey, the fact that this was so bright shows that it must be in the Milky Way, especially using my size scale for the Milky Way galaxy. Well, it turned out that that observation in the 1880s was actually of a supernova, not a normal nova. So I should mention that. But back to Edwin Hubble. Edwin Hubble had just procured use of a new telescope, the biggest telescope in the world that had just been built on Mount Wilson, the so-called Hooker telescope. Yes, I know it's a wonderful name, but the diameter of this thing, the primary mirror, was 100 inches. That made it the biggest telescope in the world at the time. 100 inches is 8 feet 4 inches, and that's 2.5 meters. And this allowed Edwin Hubble to make his first major discovery. This telescope was big enough that he was actually able to see Cepheid variables. Now, we've mentioned before that Henrietta Leavitt had actually calibrated a period luminosity relationship for Cepheid variables as standard candles. In other words, you tell me the time between peak brightness of the Cepheid variable, I'll tell you how bright the thing actually is. She calibrated this by looking at them in the Magellanic Clouds. So based on that period luminosity relationship, We know how bright it is based on how long it takes between peak brightnesses of these things. And based on how bright we know it is and how bright it appears through the telescope, you can use the equation flux equals luminosity over 4 pi distance squared to calculate and solve for the distance to at that time they called it the Andromeda Nebula. Upon doing this, the realization was that these things are really, really far away. So after calculating this distance, we realized, hey, these things are far away. Now, meanwhile, in the 19-teens, an astronomer named Vestos Slipher had found a very interesting result. When he studied all of these various spiral nebulae, he found they were all moving away from us. That's kind of weird. Maybe there's something special about these spiral nebulae. One exception, actually there were multiple exceptions, things like the Andromeda Galaxy and M33, that was another exception. These things are actually moving toward us. There's a good reason for that. They're close enough to us that they are kind of attracted by the Milky Way's gravity, and we're eventually going to capture and merge with the Andromeda Galaxy and probably eventually M33 as well. But anyway, they didn't know about that at this point. But yeah, Slipher had found that the vast majority of these spiral nebulae were all moving away from us. Now, Edwin Hubble, with his time with the 100-inch Hooker telescope, there's a picture of that mirror being hauled up the mountain road. Doesn't look like the safest road to travel up in that vehicle. But in any case, he noticed Cepheid variables not just in the Andromeda Galaxy, but also in the Triangulum Galaxy, M33, and he also found them in Bode's Galaxy, M81, the Pinwheel Galaxy, M101, as well as NGC 2403, etc., etc. And based on the period-luminosity relationships, he found that not only is M31 really far away, all these other spiral nebulae are really far away as well. They are well outside of the Milky Way galaxy. They're even farther away than what you would get by assuming that Harlow-Shapley's estimated size scale for the Milky Way was correct. So based on that, he calculated that these things were at least several hundred kiloparsecs away from, or outside of the Milky Way galaxy. So even Harlow-Shapley only had the Milky Way galaxy at a diameter of like 100,000 or 120,000 parsecs. That is 100 to 120 kiloparsecs. These things are several hundred kiloparsecs away. So that would scale up to like 1,000,000 light years away. In fact, it turns out they're actually much farther away than that, because something that Edwin Hubble didn't know is that Henrietta Leavitt's job was not complete. In other words, she had found a period-luminosity relationship for classical Cepheid variables, but it turns out there are multiple types of Cepheid variables. There are some that are dimmer and some that are brighter. It turns out that Edwin Hubble was looking at the brighter ones. Why did he end up getting the bad luck of looking at the brighter ones? Because, remember, this was relatively new technology. What happens when you have new technology, or technology that's just barely able to see things? You're going to see the things that are easiest to see. In other words, the brighter ones. And the Cepheid variables that Edwin Hubble had found are what we call W Virginis stars, which are something like a magnitude or so brighter than the other Cepheids that Henrietta Leavitt had calculated. The result is that the Andromeda Galaxy and all these other spiral nebulae are actually much farther away than we thought, and the universe is much bigger than we thought and much older than we thought, because something that we're going to get to in the cosmology discussion, the Slipher's initial realization that all these things are going away from us can actually be turned into a graph with the realization that the universe is expanding. Anyway, after Hubble started finding these things and confirming that they are well outside of the Milky Way, he realized, okay, I want to try to be a good scientist, and good scientists like to classify things in ways that might end up being useful for other people, so he developed something called a tuning fork diagram. His idea is he had ellipticals as kind of the handle of the tuning fork, and then split off. This is a classification scheme, not an evolutionary scheme, though it's debatable whether Hubble actually thought that or not. But they split off into spiral galaxies or barred spiral galaxies. And as you go along the tuning fork, the spiral galaxies go from tightly wound to loosely wound, to eventually flocculent, as we like to call them. But in any case, there is kind of this area that's kind of a merger in between what we call lenticular galaxies, lens-like galaxies. That's like, yeah, they have some spiral structure, but they also have a whole lot of elliptical structure as well. So E0 here is what we would call a perfectly elliptical galaxy, or sorry, a perfectly spherical galaxy. It would look spherical from all sides, not just because it's face on toward us, going up toward E7, where it's kind of starting to look somewhat spiral-like. Now, again, there's debate as to whether Hubble himself actually believed this served as kind of a classification system, but the truth is it did not. It does not, or sorry, not classification system, I meant an evolutionary scheme. It does, of course, by definition, serve as classification system, but it does not imply any sort of evolutionary scheme. Hubble called elliptical galaxies early type galaxies and spiral galaxies late type galaxies. Don't take anything from those names. In fact, in truth, it's kind of exactly the opposite. We had the big elliptical galaxies formed because of the merger of spiral galaxies. In other words, the big elliptical galaxies, especially the E0s, they came from mergers of, quote, late type galaxies. So again, it's a misnomer that has absolutely nothing to do with any sort of evolutionary paths that these things have taken. We're going to come back to how galaxies form later. But anyway, there were some problems. Something we'll discuss more in the cosmology discussion is that when you derive Hubble's constant from his realization of the expansion of the universe, you get an age of the universe of 2 or 3 billion years. Well, even by the 1920s, we understood from Earth's geology that Earth was well over 3 billion years old. So that would be a problem if Earth was older than the universe. But as I mentioned, this problem was eventually solved. We realized that there are multiple types of Cepheid variables, and Hubble was observing the brighter type, which are brighter than by 1.5 magnitudes. So that means that what he thought was a dimmer star closer is actually a much brighter star much farther away. This was worked out by 1950, though interestingly, one of the early people who I think had started to look into this problem of the multiple types of Cepheids was none other than Harlow Shapley, the guy who didn't believe in extragalactic galaxies, so to speak. But luckily, by the early 1950s, we realized that the universe is really, really old, much older than Earth. Now, we have some more to say on standard candles. There are a number of different types of standard candles other than just Cepheid variables. So we've already discussed parallax in a lot of detail earlier in the course. Remember, it's like you look at an object in front of your eyes, you blink back and forth between right eye and left eye, and you notice that that object moves with respect to the background. We do the same thing when Earth is revolving around the sun. We look at a close star, and that star shifts back and forth over the course of the year by a very small but now measurable amount. So we can go on from there. In fact, the Gaia spacecraft is in the process of getting us parallax distances to objects on the other side of our galaxy. And by certainly 5 or so years from now, we will have very precise distances to a lot of really distant objects. So that'll be really awesome. Now, meanwhile, one of the things that the Gaia spacecraft has been doing successfully has been finding by parallax the distances to Cepheid variables and more precisely getting more precise calibrations than what Henrietta Leavitt gave us over 100 years ago. So remember, the Cepheid variables are what we use to determine distances to other galaxies. So the better you know the calibration for the Cepheid variables, the better you're going to be able to get your distances to other galaxies. Main sequence fitting is another way that we can determine distances. The idea is that if you can use, say, parallax to determine your distance to some cluster of stars, then if there is another cluster of stars that is farther away, maybe too far away for you to use parallax, then what you can do is you just plot both clusters on something like an HR diagram, except your vertical axis will be apparent brightness. And if you make it apparent brightness, the idea is, at least if you do this with the Hyades and the Pleiades, you find that the same stellar type, like say an A-type or a G-type star will be 7.5 times dimmer for the Pleiades than it is for the Hyades. What does that tell us? It tells us that the Pleiades are the square root of 7.5 times, that is about 2 3/4 times as far away as the Hyades. So if you get the distance to the Hyades using parallax, then you just multiply that distance by 2.75 to get the distance to the Pleiades. This is not a perfect way of doing things. The Gaia spacecraft was able to get a more precise distance to the Pleiades using direct parallax observations, and they ended up extending that. I think once all the Gaia data were in, we realized that the Pleiades were something like 8 or maybe even 10% farther away than we realized, which means that maybe some of those calibrations might need to be updated on that. Though I think astronomers have done that, and there's still a little bit of a problem in terms of distance or not distance, but age of the universe agreement, something that we're going to get back to in the cosmology discussion. But anyway, yes, the Cepheid variables have a period luminosity relationship that we use. We can actually use those out almost to 100 million light years now with the best ground and space-based telescopes. Something that you can use even farther than that is something called the Tully-Fisher relation. The Tully-Fisher relation, long story short, it tells you that a galaxy that has a really big bulge is probably going to have fast spinning arms, fast rotating arms. And that makes sense. If you have a bigger bulge, then there's probably more mass there, which by gravity is going to cause things to go around faster. And there is a set of equations that have been developed for that based on, and it's a different equation depending whether it's tightly wound spiral arms like SA or loosely wound spiral arms like SC or in between like SB. The Milky Way, by the way, I believe is an SB spiral, actually an SBB because it has a bar. Anyway, there are those equations, and you, based on how bright the galaxy appears, and knowing how bright it is based on the Tully-Fisher relation. The Tully-Fisher relation is you make a spectral measurement of how fast the stars are spinning around. You plug that velocity into your Tully-Fisher relation equation, and that will tell you the absolute magnitude of your galaxy. And based on that absolute magnitude, you can turn that into an overall brightness based on how bright it looks. You do the calculation, and you figure out how far the galaxy is away. That works out to about 700 million light years. So that seems like, oh, that's really good. Here's the thing. Nowadays, hardly anybody uses this, nor do they use the Faber-Jackson relationship as much, which is basically a similar type of idea with elliptical galaxies, because we now have a good calibration for something even better, Type 1a supernovae. Remember, these things all go off at the same mass, 1.38 solar masses, assuming that it's a white dwarf that is accumulating mass from a red giant companion, which is what a lot of these things are. When they are not, when they are instead situations of two colliding white dwarfs, instead, based on the time decay of the brightness profile of the supernova explosion, you can figure out, again, how bright the thing is. These are good standard candles. And one of the things that makes them great is they can be seen up to about 10 billion light years away. That's most of the way across the visible universe. So we mentioned those problems, the fact that, yeah, if you have colliding white dwarfs, then that kind of throws things off, but you can still do a best fit type of thing. There is a lot of scatter also, and that's why we like to do best fit calculations. In other words, you find a bunch of galaxies that have these things, these white dwarf supernovae, and based on fitting a best fit line through those scattered data points, you can get an idea of how fast the universe is expanding, which is where this cosmic distance ladder is really headed. There are also some other standard candles. For example, the brightest planetary nebula in a galaxy usually has pretty much the same luminosity. In other words, you tell me the brightest planetary nebula in the Andromeda galaxy, I'll tell you how bright it is. You show me the brightest planetary nebula in M81, and I'll tell you, yep, it has that same magnitude as the one in the Andromeda galaxy. Well, based on how bright it looks, you can figure out the distance to that galaxy. Problem with that, there's a big scatter in that. I think that method is only good to like plus or minus 30%. But nonetheless, it's nice because it's a completely independent method of all these other scales. Red supergiants. These are very bright stars. In fact, the third brightest red supergiant in a galaxy is actually a pretty good standard candle. Why third brightest as opposed to the very brightest? Because the very brightest ones tend to be special. But the ones that are kind of farther down the list, yeah, they're not really as special. They're pretty much basically the same. There's also a new method that allows us to get distances to galaxies to very high precision because it is a direct geometric method. You're using something like parallax to directly determine the distance to a galaxy. Here's how it works. If you have a black hole at the center of a galaxy, and guess what? Galaxies have supermassive black holes around their centers. And if you're able to watch a clump of material go around that black hole, well, based on how long it takes to go around, well, that's the period. And based on the speed that it goes around, which you can get by breaking the light into a spectrum. In other words, spectroscopy tells you the speed. Just watching it for like a few months or a few years gives you the orbital period. That tells you the radius of the orbit. Well, now you know the exact radius of the orbit. Based on knowing the actual radius of the orbit, I shouldn't say exact because there is uncertainty in this velocity measurement, but it's like 1 or 2%. Based on that known radius of the orbit now, well, from how big the orbit looks in your telescope, in other words, the angular size of the orbit, well, angular size times distance is equal to the actual radius of the orbit. So you get the distance by taking the radius and dividing by the angular size. That is I guess what you really want to do though is take the known diameter of the orbit and divide by the whole angular size of the orbital ring. That's probably the easier measurement to make instead of dividing by 2 each time. But anyway, that's how astronomers can get pretty precise distances out to galaxies, potentially with error bars of only about 2 or 3%, out to about 7 billion light years. Unfortunately, we don't always have the right viewing angle to be able to do this. So to date, I think this has only been done with a few galaxies, but it is a proof of concept. So now I invite you all to kind of pause the video and discuss, maybe with somebody around who also happens to have seen this. If you pretended that Earth, instead of having this positive curvature, such that it was curved like a sphere, pretend that it was kind of inverted in a way, such that objects instead of disappearing below the horizon, they would actually rise very gradually above the horizon. Discuss how, living in a small town, you could derive basically an American distance ladder for use in estimating the size of the United States without actually leaving your town. This is a little exercise that I got from Mark Whittle's great course, Introduction to Cosmology, which is a really nice course talking about cosmology in detail at various levels of rigor for the various listeners and watchers anticipated for the course. But this is one of those cool little questions that I came across, and that's like, yeah, this is something I should use in class. So yeah, take a minute to pause, think about things like standard candles that you might use for doing this, but remember, you're not allowed to leave your small town. Okay. So after you've done that, let's move on and unpause. Galaxy types. As we saw, Edwin Hubble came up with this classification system for galaxies, and in his tuning fork diagram, he had ellipticals and spirals, and he divided the spirals into barred spirals and non-barred spirals. But there were also some galaxies that just didn't fall in the tuning fork. These were irregular galaxies. But first, let's turn our attention to spiral galaxies. These are ones that have noticeable kind of spiral structure or general disk-like structure with spiral patterns in the disk. And the spiral arms, we discussed it before when talking about the Milky Way. These seem to result from waves of overdense regions propagating outward. Like maybe something happens in the center of the galaxy, like the black hole has this big outburst of material, and that creates a density wave that propagates outward over time. But as that happens, it's interacting with other material that's in orbit around the galaxy, causing some of that to collapse. And boom, you get nice, bright, blue, hot star stars and other nice red star forming regions. So those go into orbit, and then the wave keeps going out, and it encounters other material, and same thing kind of happens, but that's happened later, which is why instead of having the arms just go straight out, they end up having a spiral structure, because the stuff that's closer ends up completing orbits more often than the stuff that's farther away. But this doesn't last forever. Eventually, that kind of diminishes out somewhat, though the spiral arms themselves do have a little bit more gravity than the other regions, so they can live for like billions of years before anything bad happens to them, and they kind of fade away. In fact, more often what happens is the galaxies end up colliding with other galaxies, which ends up screwing everything up. We're going to get to that later. But in any case, remember, the spiral arms generally trail the stuff that's actually in orbit. In other words, gas and dust goes through the spiral arms and then ends up getting compressed, which helps with more star forming region, as opposed to the other way around. The spiral arms, the spiral structure itself takes a longer time to complete a full loop around the galaxy than do the stars and the gas and the dust. So here is a very nice spiral galaxy, though you don't really see so much in the way of direct, obvious spiral arms with the Andromeda Galaxy, but it would certainly be classified as a spiral galaxy. And it also has two elliptical galaxies orbiting it. It has this nice dwarf spheroidal galaxy, an E0, called M32 right here. So Andromeda Galaxy is M31, this one is M32. This galaxy right here is not M33, it's actually the last object in Messier's famous catalog. It's M110. And this, I don't know, is maybe like an E5 or an E6 dwarf elliptical galaxy. So remember, dwarf galaxies are quite common around big galaxies. The Milky Way has about 60 dwarf galaxies orbiting around it, and that's just the ones that we know of, the ones that we've discovered. And they're generally dwarf elliptical, dwarf spheroidal, though a lot of them are also irregular because they're in the process of being eaten and torn apart. I do want to show you a really cool video of the Andromeda Galaxy that was taken by, well, it was made based on a very high-resolution picture taken from the Hubble Space Telescope. So as you watch, pay particular attention to a lot of the detail, like the occasional background galaxies visible through the star fields, as well as the occasional globular clusters. The Andromeda Galaxy probably has around 500 globular clusters. That's over twice as many as the Milky Way has. So let's watch that video, and I'll give some commentary as we go through it. So here comes the video, and I'm going to unpause this. So zooming into the Andromeda Galaxy, that's a similar picture as what we just saw, and you can see the two orbiting galaxies, M32 and M110. Of course, it has a lot more than that, but most of them are small. And as you see at the bottom, the picture itself that was made with the Hubble Space Telescope, or actually the array of pictures, is composed of over 1.5 billion pixels. So do you have a 1.5 gigapixel camera? So notice now we're zooming in, and this is where, so a lot of these stars that you see, these bright ones, these are Milky Way foreground stars, but now we're close enough that you can see the countless individual stars, similar to what Galileo would have seen with our own galaxy when looking at it through a telescope back in 1609, 1610. So here you have these countless individual stars. Notice occasionally you see here's probably a background galaxy and another background galaxy that you can see kind of through the star field. But eventually we're going to get into an area that's too dense to be able to see that. And sometimes you'll see star clusters, like there's a nice star cluster. That might be a baby globular cluster here, though we will see some globular clusters that are bigger. And here's that background galaxy that I was mentioning from before. And that might be a globular cluster right there going off the screen. And here's a Milky Way foreground star, but wow, just look at these countless individual stars. There's another Milky Way foreground star, some nice star clusters there. That might be a globular cluster. There is a globular cluster right there. That's a very nice globular cluster. And just panning through and seeing, yeah, it's looking a little bit blurry because of the way the video is, but we have just countless individual stars. The Andromeda, there's a very nice globular cluster. The Andromeda Galaxy has around 1 trillion stars. So the Milky Way has about 400 billion. the Andromeda Galaxy, it's a bigger, more evolved galaxy than the Milky Way. Now we're getting closer to the core region, and you just have incredible numbers of stars here. This is, I'm actually going to pause this just so that we can see this. Just look at all of these stars. You're also seeing some dust here. We're seeing some dust here. These areas that are kind of brown. Here you have some reddening occurring. Apparently we have a real bright star behind some of this dust right here. Just awesome, awesome picture. And again, Milky Way foreground stars right here. So continuing in with this motion, here you see a lot of dust showing up off to the right side of the picture, some more dust coming in, until eventually we're getting close to the actual nucleus of the, or at least the bulge of the galaxy. And just countless stars, a really, really awesome picture. This is what it's like to zoom and pan around a spiral galaxy. So if there was any doubt that these things were star forming or regions of countless stars way outside the Milky Way, this picture would have been great proof of that back 100 years ago when Shapley and Curtis were having their great debate, as it was called. Because here in this picture you can just see all of these countless individual stars, and the realization here is that this is a complete island universe way outside of the Milky Way. But even so, it is our nearest large neighbor. And that's it for the video. So going back to our discussion, here's an example of just your prototypical face-on spiral galaxy. Notice that you have some dark dust lanes around as well, but you have very clear, nice spiral structure. This is your so-called spiral nebula, except we now realize it's an island universe, a spiral galaxy. Here's a Hubble Space Telescope picture of a spiral galaxy where one of the, it looks like there's something kind of weird with this. Like something's happening here, breaking off of arms and stuff like that. Well, here's the thing. One of these arms is actually a leading spiral arm. It's rotating faster than the rest of the material in the galaxy. That's rare. Usually spiral arms are trailing arms. They rotate slower than the actual material that composes them. In other words, the material composing them is actually simply passing through, and then it enhances the arm as star formation occurs as that material passes through. We've also mentioned that the Milky Way is a barred spiral galaxy. In fact, 2/3 of spiral galaxies are barred spiral galaxies. Here's a nice barred spiral. There's another nice one. That's NGC 1300, a rather famous one. This is a Hubble Space Telescope picture. But the great thing about spiral galaxies is there are lots of them out there. Many of them are similar to the Milky Way, so studying them in detail can tell us potentially more about the Milky Way and really how it looks, because we live in the disk of the galaxy. We can't see it from above. We can't travel tens of thousands of light years above the disk of our galaxy or below it in order to be able to see it face on. So we look for other galaxies that we can see face on to try to understand our home a little bit better. So now let's turn our attention to elliptical galaxies. Elliptical galaxies are a bit more boring. I could show you 1,000 pictures of elliptical galaxies, and after you've seen probably about the first 5, you've pretty much seen them all, except for a few special ones that we're going to get to. This is your typical reasonably large elliptical galaxy. Now, the way that these form in comparison with spiral galaxies is early in the universe there were a lot of very overdense regions which ended up collapsing to form galaxies and galaxy clusters, stuff like that. But where the galaxies ended up forming, if that collapse happened really fast, then the result was that you got a supermassive black hole very quickly in your galaxy, your newly forming galaxy's core, and that would end up becoming a quasar because it would be feeding off of lots of gas and stuff like that. We're going to talk about that later. And this quasar would end up ionizing the surrounding area, and that ionized gas, well, ionized gas can't really form into stars because you can't radiate this material so much, or sorry, you can't radiate off this energy so efficiently as it collapses, so the collapse doesn't happen. So if that happens really fast, you're going to get an elliptical galaxy because the stars that have formed have not really had their orbits dragged into any sort of order, like going around in a disk pattern. Whereas in the case of spiral galaxies, this is where the star formation happened a little bit more slowly, and the black hole at the center of the galaxy, it didn't really turn on, at least not enough to really ionize all of that gas, so you kept having that star-forming activity, and the gas stayed neutral. Well, this neutral gas, what it can do very effectively is can actually help to provide a little bit of friction to the stars as they are orbiting around and kind of corral them into a general disk-like structure. And later on that can be disrupted when they collide with other spiral galaxies, giving you elliptical galaxies again, but still, it's something to keep in mind in terms of how they formed to begin with. This is a giant elliptical galaxy. The centers of clusters of galaxies tend to have giant elliptical galaxies, what we call CD ellipticals, central dominant ellipticals. And these are very, very big galaxies, sometimes with multiple trillions of stars in them, and they often have really big black holes as well. I forget exactly which galaxy this is. I think this might be the one that's at the center of the Perseus supercluster of galaxies. Now, there are also irregular galaxies. These things are often really cool because they're, well, irregular. In this case, we have a very new galaxy. In other words, it's just so happened that the various tidal forces have occurred to cause star formation to finally start in this area, and you have this big burst of star formation, this nice starburst galaxy, as we call it. Oh, and look, here we have this nice distant spiral galaxy in the same picture. In fact, this is a Hubble Space Telescope picture that really zoomed in on this thing. You can actually see lots of background galaxies just all around. Here is also an irregular galaxy. This is a famous one, in fact. This is M82. In fact, it's right next to M81 in Ursa Major. In fact, they are interacting with each other, at least they interacted with each other, and when M82 flew by M81, or however you want to think of it, maybe the other way around, but in any case, that the tidal forces from M81 triggered a big burst of star formation in M82 and disrupted it a bit, and this red hydrogen gas that you see getting spewed off here is due to the fact that this is a starburst galaxy. It has lots of supernovae. It has supernovae much more often than your typical galaxy, and the shocks and winds from these supernovae and very active star-forming regions are blowing off this gas right off into intergalactic space. You might wonder, it's like, well, how do we know that this is an irregular galaxy as opposed to just an edge-on spiral galaxy? Well, here's the thing. If it was an edge-on spiral galaxy, the stars on one side of the galaxy would be moving away from us, and the stars on the other side of the galaxy would be moving toward us as they all orbit around the central area. That's not what's happening here. These orbits are random. Some other nice features of galaxies include the fact that it's actually possible to estimate the mass of the central black hole of a galaxy based on the size of its bulge. And if you think about it, that kind of makes sense. A galaxy that has a really big bulge relative to the size of the rest of the galaxy is one where you're talking about relatively random orbits. That's the result that you get after multiple mergers with other galaxies, and multiple mergers are going to tend to result in multiple big black hole mergers, and you're going to get a bigger black hole accumulating at the center of this galaxy. So Bode's galaxy M81 actually has a 70 million solar mass black hole. The Milky Way, though, it has a much smaller bulge than this. The mass of its central black hole is 4.5 million times the mass of our Sun. On the other hand, M33, the Triangulum galaxy, has basically no bulge at all. And guess what? As far as we can tell, it doesn't have a central supermassive black hole. More precisely, we have an upper limit for the mass of any central black hole at about 1,500 solar masses, but we have not found, as far as I know, any evidence of a central reasonably massive, I guess that would be an intermediate mass black hole. But nonetheless, it's a very exciting galaxy. As you can see, it has some nice star-forming regions. There actually is one that I'd like to take a moment to talk about in particular, this one down here. This one is called NGC 604, and it's one of the biggest star-forming regions that we know of in the local universe. It's like the first or second biggest star-forming region in the local group of galaxies, which includes the Milky Way, the Andromeda Galaxy, and M33, the Triangulum Galaxy. That's what we call the local group of galaxies. And anyway, If you were to place NGC 604 at the same distance from us as the Orion Nebula, think the Orion Nebula, if it's a real dark night, you'll see a little bit of fuzz in the sword of Orion, and that marks the visible part of the Orion Nebula. Well, if you put the visible part of this in the same area of the sky and at the same distance as the Orion Nebula, well, first of all, the area from the bottom to the top would stretch 60 degrees across the sky, and you'd be able to see it. Second, the whole thing would actually be brighter than Venus. It would actually cast a faint shadow at night. Its apparent magnitude would be something like -5.5. It would just be an incredible sight in the night sky. Just imagine what that would have looked like to ancient civilizations and everything as they're contemplating the heavens and why we're here and stuff like that. Now, turning our attention to galaxy formation, throughout much of the 20th century, there's been a lot of debate about what formed first, whether it was large galaxies that eventually split into small galaxies, or the other way around. We call this the top-down versus bottom-up approach. But with the Hubble Deep Field project, where the Hubble Space Telescope would spend hours or days just staring at the same dark area of the sky and continuing to accumulate data to form our impression about what the universe is really like, we realized that it's actually the small galaxies that form first. So here is a deep image taken by the Very Large Telescope that shows some older galaxies, and it's faint because you have, not very high resolution here. We're looking at a very small region of the sky, but notice this is kind of like a spiral galaxy kind of trying to form, but it's not quite together yet. You could think of this as a proto-galaxy, and this is actually mainly gas. This is mainly gas that's been ionized by the light of a lot of this other stuff, and it's kind of maybe eventually going to try to form into a spiral galaxy. Over here, you might wonder, is like, oh, well, that looks kind of like your edge-on spiral galaxy, or maybe a E7 elliptical galaxy, or something like that. Well, maybe you're right. Here's the thing. It's way smaller than galaxies today. That's something that can be measured. Here is actually a nearby galaxy. It's called 1Zwicky-18. It's a newly forming galaxy that it just so happens that the mass has reached what we call the Jeans mass, which is where the pull of gravity inward overcomes the outward push of gas and radiation pressure. So this Jeans mass has been overcome, and the thing collapsed all at once to form a bunch of really hot young stars. It's a really cool picture. Now, early in the universe, galaxies more often tended to be irregular in shape, but stars formed much more rapidly back in the early universe. So this is a picture from the Hubble Ultra Deep Field showing what galaxies looked like in the early universe, and we're not talking about these big things that you see here. The big things are galaxies that are, quote, only a few billion light years away. What we're really focusing on here are the little points of light. These little points of light, some of these have been studied in more detail by bigger ground-based telescopes, and they are very, very, very far away. As they've been called by some people, they're kind of like galaxy chips. They are in the process of eventually forming what you might call mature galaxies, but these are mostly small, irregular galaxies. Every once in a while there will be some news article about how astronomers have discovered a very mature galaxy in the early universe, say 2 billion years after the Big Bang or less, and it's like, hey, this mature looking spiral galaxy. But again, those things are still much smaller than the galaxies today once you work out their distances using the Hubble redshift, and then figure out how big they are based on how big they look, and figuring out the distance and taking into account the curvature of space that's occurred as the universe has expanded, stuff like that. But anyway, this is a really awesome picture, and just about every object in here is a galaxy. There are a few exceptions. There's a Milky Way foreground star, there's a Milky Way foreground star, and I seem to recall that there are a few others, but they don't really make themselves very obvious in the picture. In fact, I think this is another one right here. So we've already mentioned the differences in how they form. In the case of a slow infall of gas, you're typically going to be dealing with a situation that's eventually going to turn into a spiral galaxy. So it's like, yeah, you might get something that starts off as elliptical or irregular, but you're going to end up getting density waves that end up helping to form spiral arms, and this kind of helps to uh, even out these random orbits that you would otherwise get from your elliptical galaxies, because you have these over-dense regions that end up slowing that down. However, if the collapse happens too quickly, which is what you have in regions that are very dense, you're going to end up forming elliptical galaxies. However, once you form spiral galaxies, these things, remember, they're a lot smaller than spiral galaxies today. They interact with each other, they merge, and that creates, because, I mean, a merger is a relatively messy process, we're going to see some of that very soon, that creates an elliptical galaxy, a situation where the stars have relatively random, long elliptical orbits, but randomly oriented along random axes. So further collisions give you even bigger elliptical galaxies. However, if there's enough gas left over after these mergers, then what will happen is these elliptical orbits, they'll eventually kind of get slowed down as the stars go into the where a lot of the gas is, and eventually you're going to end up getting spiral structure again. So there is this evolution also occasionally from elliptical to spiral. However, once most of the gas is gone, or once that star forming has pretty much stopped, that's going to stay an elliptical galaxy. For example, the galaxy M87, or that Perseus A galaxy that I showed you at the beginning, those are not going to become spiral galaxies again. They're always going to stay elliptical galaxies. So as I mentioned, there used to be a lot of debate about what structures formed first, but now we realize that it's the smaller galaxies that formed first, helped along by cold dark matter, something we're going to discuss when we talk about cosmology, and then they interacted with each other to form larger galaxies. So yeah, there are contributions from both of these bottom-up and top-down scenarios that help us to understand galaxy formation, but at least in terms of what actually happened, we realize it's the small little galaxy chips that formed first, and they ended up combining to give the bigger galaxies of today. Things like the Milky Way are the result of lots of galactic cannibalism, as it's often called, and we are still in the process of doing this. We are tearing apart the Sagittarius dwarf galaxy, poor thing. I should mention that this kind of what formed first, chicken or egg scenario, there's a similar debate concerning black holes nowadays. So I do want to talk about that because that's important for our discussion about galaxies. We know that galaxies, except for M33, harbor supermassive black holes at their centers. And if they have any sort of bulge at all, then they definitely have supermassive black holes. Well, where did these supermassive black holes come from? Did they come from a situation where you had your typical life cycle of star, the stars with more than 20-something solar masses eventually left behind black holes, and then those black holes found their way toward the center and merged together? That was how we pretty much imagined things for a long time, and that seemed fairly reasonable, because think about it this way. These black holes are massive objects, and when you have a massive object interact with a less massive object via gravity, what usually happens? Well, the less massive object tends to increase its velocity. It gets flung out, while the more massive object tends to get slowed down. It doesn't really get moved much, but it gets slowed down. So this ends up resulting in the black holes typically falling toward the center of your galaxy over a long period of time, because they're just the more massive objects. In addition, you have a concept called dynamical friction, where as the black hole, or whatever it happens to be, it works for anything, orbits around, it ends up attracting objects to it, especially if it's really massive. It attracts objects to it quite efficiently, but by the time those objects actually converge on where it was, well, it's moved on. So they end up converging on an area that's behind it. But as such, they end up exerting gravity on the black hole or whatever it was, tugging it back and slowing it down, meaning that it ends up getting sent toward the center anyway. That's the old idea. But the new scenario is a situation where maybe you have a really big cloud of gas, a very dense region of gas that collapses directly into a black hole at the center of what will eventually become your galaxy. So, recent observations have revealed evidence of large, dense gas clouds collapsing directly to supermassive black holes. In other words, we realize these things are not going to end up forming stars. These things are actually massive enough that they're probably going to end up collapsing directly into black holes. So in this case, these are images from the Chandra X-ray Observatory and of early gas clouds like over 10 billion light years away. Remember, something that I've reminded you countless times throughout the course: astronomy is the only field of science, in fact, the only field of anything, in which it is possible to directly observe the distant past. In every other field, anthropology, archaeology, geology, etc., you are observing relics left behind in the past. But in astronomy, because of the finite travel time of light, you are directly observing the distant past when you look at how the universe appears 12 billion light years away. That's telling us what the universe was like 12 billion years ago. So as we mentioned, galaxies evolved. The first galaxies that formed typically had masses on the order of about 1% the present-day mass of the Milky Way. And they also had a higher proportion of massive blue stars, because remember, you didn't have things like metals to dissipate this kinetic energy, this radiation that's occurring as the gas cloud collapses. So that means that the collapse is slowed down, which gives time for the dense regions to merge together, and you tend to get a few really big stars as opposed to more smaller stars. So that's why we end up getting, at least one reason why we get lots of heavy elements from early in the universe. And we also now realize that the evolution of galaxies is often driven by the evolution of their central black holes, because as gas gets sent toward the center, that black hole is feeding off of the gas. That creates a quasar for a time. We're going to talk about quasars very soon. Be patient. But after that gas has been used up, the quasar turns off. And there might be relatively little gas left over for star formation in that case. Or that quasar itself had jets, and these jets ended up ionizing all the surrounding gas, not just in the galaxy, but actually in the entire cluster of galaxies, which is why, or at least that could be one reason why you have two different types of clusters in the universe. You have smaller clusters that are composed of mainly spiral galaxies and their orbiting dwarf elliptical galaxies, or you have bigger clusters that are mainly composed of larger elliptical galaxies and their orbiting galaxies. There are these galaxies that are called red and dead galaxies. These are, for example, the centers of large galaxy clusters tend to have giant elliptical galaxies, and these often have trillions of stars in some cases, but very little star formation. So in other words, no blue stars. The stars there are kind of orange or redder in color. You're dealing with, if you have bright stars, they're probably red giants in the latter stages of their lives. And the other stars are dimmer stars, but they're very old, so you're talking about stars that have smaller masses than the sun in a lot of cases, and what that means is that they're probably cooler in temperature, again, red in color. Edwin Hubble cataloged lenticular galaxies, which we mentioned are kind of a combination of elliptical and spiral galaxies. A lot of times after a recent galactic merger, you'll be left with a lenticular galaxy, depending on the sizes of the galaxies involved in mergers. Here's an example of a lenticular red and dead galaxy. And I'm sorry, this galaxy, unfortunately, is not really going to form much in the way of any more stars. This is a very distant galaxy, I should mention. Here's another lenticular galaxy. It has lots of dust left over from previous generations of stars, but not much in the way of gas. It's not going to form many more stars, and it's dead. That's it. Now, what about these quasars that we have been mentioning? We introduced them a little bit back when we talked about black holes, but now's the time to go into a little bit more detail about these things. So, what are quasars? They stand for quasi-stellar radio sources, and the idea is that back when they were first found, they appeared as just points of light in telescopes. And they also, though, had very strong radio signatures. Radio telescopes had found these things, and that's like, oh, there's a really strong radio signature there. Let's look at it through a telescope. But they look at it through a telescope, and it just looks like a star. But when they perform spectroscopy on this quasi-stellar object, QSO as it was termed then, they found that these things had very large redshifts, meaning that, again, we're going to talk about this in more detail when we discuss cosmology, that they are located so far away that the universe has expanded a good bit since the time their light was emitted. So that, in other words, their spectral lines are very significantly shifted toward the red part of the spectrum. But the spectra themselves had a lot of similarities and some differences with certain types of active galaxies. Now, I will mention that now the mystery is solved. I mean, in the 1990s, the Hubble Space Telescope found that these things are actually the cores of very active galaxies. In fact, here are some of these pictures. And again, we discussed a lot of this in other detail in our black holes discussion, but in this case, in a lot of situations, they have successfully been able to blot out a lot of the light from the central quasar itself, and yeah, you find that these things are actually just at the centers of active galaxies, particularly spiral galaxies that appear to have recently undergone mergers. In other words, you see, it's like, yeah, you have some spiral structure here, but it's kind of a little chaotic here. Well, that's what you expect after a merger, where you've had a large amount of gas shoved into this. Again, these things are cosmological distances away, which means we're looking at objects that existed when the universe was a very different place than it is today. And these things had a lot more gas in order to that was around to be able to form stars, but in the case of galaxy mergers, a lot of times this gas would end up getting shunted into the central supermassive black hole. Well, as that gas falls into the central black hole, you're talking about a huge conversion of gravitational potential energy into kinetic energy. You actually get a lot more energy out of this than you would get if you simply collided antimatter and matter of the same mass together. That's why these things are so incredibly bright, because you have a huge amount of gravitational potential energy all going to kinetic energy as it gets closer and closer to the black hole and eventually ends up falling in. But the light is emitted, of course, before the gas falls into the black hole, but it's colliding with itself really strongly because it's going so fast, very hard collisions, getting heated up X-ray hot, gamma ray hot, and you get just lots of emission through all parts of the spectrum from this situation. These are an example of active galactic nuclei. So you have an object where a central black hole is actively feeding on gas. It could be gas that was shunted toward there from a recent galaxy merger or early in the universe as the central supermassive black hole was forming and then pulling in a lot of the rest of the gas, or a situation where a large star has passed close to that black hole and the black hole has shredded that star due to the tidal forces. That's one of the other reasons why you don't have quasars around today to speak of, because first of all, you have a lot less gas that's able to go into these things, but second of all, a lot of these central supermassive black holes, nowadays they have become so big that they don't actually shred stars. They actually gobble the stars up whole because they're so big that the star can go in their hole without getting shredded, and boom, it's in the black hole. So we don't know anything about what happens after that. Just the black hole gets bigger. So in any case, you're dealing with a situation where you have a black hole that is actively feeding, hence we call it an active galactic nucleus, but the angle at which you observe this is what actually determines what you see. So there are three basic types that we consider. We consider radio galaxies, we consider quasars, and we consider blazars. And this unified model has come to the conclusion that generally speaking, most of these things are the same general type of object. So a radio galaxy is what you get if the central bright accretion disk around that supermassive black hole is blocked by the dust torus that is also part of that accretion disk. You also end up pulling in a whole lot of dust, and that dust ends up forming a ring around it, and basically a donut shape is what we call a torus. However, if your line of sight avoids that dust torus and you're able to see the accretion disk itself, that really bright, hot X-ray, gamma ray emitting accretion disk, then we observe a quasar. again, it's a really, really bright object because you're talking about this incredible conversion of gravitational potential energy into kinetic energy as that gas goes into smaller and smaller, faster and faster orbits. Now, the thing itself, interacting with that black hole, this gas is going around so fast it creates very strong magnetic fields because this is ionized gas. These magnetic fields end up corralling charged particles into a beam that ends up coming off poles, so to speak, very close to the black hole itself. And these jets of material, if it just so happens that that jet of material is directed toward Earth, and we look down that jet, we are viewing what we call a blazar. So here is a picture kind of summarizing all of this. So if we're looking at it from the side of the dust torus, we observe a radio galaxy, because once this jet ends up going off into space and then expands outward, we're talking about synchrotron emission of radiation, and you get a lot of radio emission from that. A great example of that is the galaxy Cygnus A, which is one of the brightest radio sources in the sky, in spite of the fact that it's 250 million light years away. And in the case of a quasar, well, that's what you would get if you were to view this just kind of as we're viewing it on the screen. You get to see the central accretion disk and you see a quasar. However, if you're looking right down the axis of this jet, then you see a blazar. This thing is much brighter than your typical quasar due to the effects of special relativity. A lot of this material is moving at a very high percentage of the speed of light, but when material that's moving at a high percentage of the speed of light is directed toward you and a little bit off axis from you, then it appears sometimes like it's moving at super relativistic speeds, like higher than the speed of light from side to side. That's an illusion based on that effect and everything, but it's still kind of interesting. But in any case, that situation, you're going to be viewing it with a lot more energy down the axis of that jet, and you're going to view a blazar. And these things, due to those special relativistic effects, tend to oscillate in brightness very, very quickly. And this is also one of those reasons why astronomers realized relatively early on that quasars probably have something to do with a black hole, because the changes in brightness happened over a reasonably short period of time in a lot of cases, but that can only happen if you're talking about accumulation of stuff onto a small object. But that small object is causing this stuff to have a huge amount of energy, so a black hole seems to be a good candidate in that. And that has since been confirmed with more refined observations. Now, cool discovery. In 2017, a very high-energy neutrino was detected by the ice cube detector in Antarctica, and when supercomputers traced the path of the particles that created that neutrino, that allowed scientists to pin down the blazar with the nice romantic name of TXS0506 plus 056 as the probable source of that neutrino. It's a blazar 3.8 billion light years away, and that's actually that is close as blazars and quasars go. Most blazars and quasars are on distances on the order of like 10 or 11 billion light years away when the universe was a fraction of its age today. So, as I mentioned, eventually these quasars either consume enough of the gas in their galaxies, or they become big enough that instead of shredding stars, they just eat them whole, that eventually they turn off. That's one of the big reasons why we do not have quasars around to speak of today. They were common in the early universe, not so much nowadays. This was actually one of the big pieces of evidence in favor of Big Bang theories that was discovered in the 1950s. In the 1950s, scientists using radio telescopes realized that there were these radio galaxies that seemed to be pretty far away, but they were quite different from galaxies today. And the fact that you had galaxies that seemed to be farther away that were very different from nearby galaxies indicated that at longer time spans earlier in the universe was a bit of a different place than it is today. Well, that's exactly what you would expect in the case of Big Bang theories, where the universe came into existence, or at least a phenomenal period of expansion began about 14 billion years ago. Whereas, in contrast to the steady state theories, which were the other big theories of cosmology that were popular in the 1950s, they stated that the universe had been around forever and that there weren't really any special periods of time in the universe, and that as you look deeper into the universe, things should pretty much look the same. Well, in the 1950s, we started realizing that that's not the case. But the nail in the coffin for steady state theory came in the 1960s, and that's what we're going to talk about when we discuss cosmology next time. Now, in terms of citizen science, crowdsourced projects have led to greater understanding of galaxy black hole evolution. And in 2007, there was a really neat situation where a Dutch school teacher was participating in citizen science and found that there was this strange green object in the Sloan Digital Sky Survey. And the idea of the project itself was to just give, this was the Galaxy Zoo project, and basically if you participated in it, then you'd get these images of galaxies, and using Hubble's classification scheme, you would classify these galaxies. This was considered important because a lot of surveys had been done. For example, in this case, it was from the Sloan Digital Sky Survey, and the data were coming in much faster than the project leaders and their colleagues were able to analyze them. So they outsourced these data to citizens with instructions on how to classify these things, and the idea is that basically using the citizen science and these results that they got back, these would already kind of be somewhat pre-classified based at least on numbers and all of that. Well, when this Dutch school teacher, Hanny van Arkel, when she found this object, it's like, okay, fine, you have a nice kind of spiral lenticular galaxy, but I don't care about the spiral lenticular galaxy. What in the world is this green running man thing holding some bottle of I don't know what down here? So she got discussions going on that, and based on those discussions, the Hubble Space Telescope was enlisted to take a better picture of this, and the realization is that this was intergalactic gas that was being ionized by maybe a quasar or something from around the core of this galaxy. And we now realize that there are other ones that are like this as well. So this original object is now named after Hanny's voorwerp, Hanny's object, and this got a new study going in these types of objects, which was, I think, really cool. As we've mentioned, galaxies tend to interact with each other over time. These interactions can be quite spectacular. This is a case of the antennae galaxies, NGC 4038 and NGC 4039. They are in the process of interacting with each other, and as that's happening, the tidal forces from these galaxies on each other are compressing regions of gas and causing them to collapse and form stars. When galaxies collide, if there's enough gas left, then there will be big bursts of star formation. You're talking about a lot of hot young OB stars, a lot of which are going to end up going supernova. Oh wait, we can kind of see that here. Look at all this dust being spewed off by probable supernova explosions that have occurred during this interaction. Galaxy interactions take billions of years. A star that goes supernova is only going to live for a few tens of millions of years, if that. Here's another nice galaxy interaction. In this case, notice there's this stream of material from this galaxy. This is something called a tidal tail. We're going to get to that soon. Here's another situation where you have this nice tidal tail. These two galaxies are called the mice. Very nice image taken from the Hubble Space Telescope. You can really get a sense of the scale of the universe here. These things are tens of millions of light years away from us, and yet you can see a lot of these really little galaxies in the very distant universe in the background here. It's like these are the main stars, but then you have this crowd that's way, way far away. These tidal tails occur when you get these streams of gas that are kind of pulled off due to the tidal interactions, but as these streams of gas are pulled off, they compress and they end up forming stars. There's also dynamical friction. We've talked about this dynamical friction before, how you end up getting big massive black holes in the cores of galaxies as one way that they can form from as a merger of smaller black holes that end up accumulating there by dynamical friction. Well, this dynamical friction is really important when you're talking about galaxies, because galaxies are not solid objects. They are just big gravitationally bound objects of up to trillions of stars in some cases. So what happens is, as they go by each other in their first pass, well, the tidal forces end up dragging material behind, and that material from one galaxy that gets dragged behind that galaxy ends up slowing it down, as opposed to just drifting by and deflecting due to the interaction. If it was two planets interacting, they would kind of drift by, deflect, and go off course, but they wouldn't end up coming back. But in the case of galaxies, you're talking about things that are pulled apart as they get deflected, and that pulling apart creates new gravitational forces. So that's, again, the same situation behind how you may get central supermassive black holes at the cores of a lot of galaxies. I should also mention that when galaxies collide, stars don't, because the typical distances between stars are on the order of light years. That is, on the order, like a light year is about 9.46 times 10 to the 15 meters, so that rounds reasonably close to 10 to the 16 meters, that is 10 quadrillion meters, 10 trillion kilometers. But a typical star has a size on the order of about 10 to the 8th meters, or 100,000 kilometers. Well, that shows us that and again, this is just one dimension. I mean, these collisions, if they occurred, happen in 3 dimensions. So when galaxies collide, star collisions are extremely rare. Very, very rare. They do occasionally happen, but we're talking about like a few stars in the core of one galaxy, where the stellar densities are much greater in the first place, colliding with a few stars in the core of the other galaxies. So generally speaking, stars just go on their merry way. The Milky Way and Andromeda are on course for a collision. We now realize that in-spiral will begin happening in about 4.5 billion years. And when that happens, things are really going to be awesome. This is how the night sky might look on a dead planet Earth about 4 billion years from now, as the Milky Way and Andromeda kind of make their first pass in that collision. So can't wait. So let's hope that we can extend our lives for about 4 billion years so that we can see this. And these frames show other intervals of that collision. For example, here is what it looks like right now. There's the Andromeda Galaxy. This is kind of a nice overexposed image of the Milky Way. But then, maybe in couple billion years, the Andromeda Galaxy is going to be a lot closer to us. We are approaching the Andromeda Galaxy. It is a direct approach. There's not really any side-to-side motion. The Milky Way and Andromeda are in direct collision. They are on a direct collision path right now. That's not going to change. So then this is how it might look, say, in about 3 billion years. And then here we're talking about what's going on after that first pass in about 4.5 billion years. And then as that occurs, things are going to get more exciting, because they're going to have a pass by, but then remember that dynamical friction, that's going to slow down both galaxies, and they're going to end up going in reverse, and they're going to pass each other again until after a while they eventually merge and say like about 7 or 8 billion years into a big giant elliptical galaxy with perhaps a couple of trillion stars. When you include the 1 trillion stars in the Andromeda Galaxy, the 400 billion stars of the Milky Way Galaxy, and the stars that are going to be produced as a result of this collision. So that's really cool. I do want to show you a little video that has been made from a computer simulation on this collision. So this video is on Andrew Rader's YouTube site. So here we have the Milky Way and Andromeda Galaxy. There we are after the first pass of this collision, and notice these tidal forces really pulled off a lot of material, and you got this big burst of star formation out here. You saw that density wave end up going outward. That actually helps to give some spiral structure in the meantime, but that we're not done yet. Here comes the second pass, and now we have this big merger in here. Matter getting flung everywhere, big bursts of star formation going out everywhere into space. You have all these tidal forces and these tidal tails, with just an absolutely spectacular event in this case. So again, can't wait. It's going to start in about 4 or 4.5 billion years, and it's going to last for a few billion years. And the end result of this is going to end up being a lenticular galaxy or a giant elliptical galaxy in that particular collision. Now, I say that particular collision because M33 is probably going to be part of this as well, though while the Andromeda Galaxy and the Milky Way are in the process of their collision, M33 is going to kind of go drifting by, but it's going to get pulled back, and eventually we think that M33 is going to end up merging with this merged galaxy Milky-Andromeda, if you want to go by that name, and end up giving an even bigger galaxy. So I don't know, a combination of Milky-Andromeda and Triangulum galaxy, like Milcomulum or something like that. But that'll be probably about 8 billion years from now or so. Now, galaxy clusters. Isolated galaxies are very rare in the universe. The vast majority of galaxies belong in clusters. So the Milky Way is part of the local group, and we've already mentioned how the Andromeda Galaxy, that is M31, and the Triangulum Galaxy, M33, are the other two big galaxies in the local group. And the Milky Way and Andromeda make up the vast majority of that mass, at least the Milky Way and Andromeda, including their dark matter clouds and stuff like that. We make up the vast majority of that mass. M33 is much smaller, but still it's a reasonably sized galaxy. M33 itself is much, much bigger than any of the other satellite galaxies that make up the galaxies in the local group. Galaxies and clusters, they grow by mergers. So the galaxy at the center of a large cluster is usually extremely massive. It's an elliptical galaxy. It'll typically have 10 to 20 times the mass of the Milky Way galaxy. And sometimes the black holes that are in the centers of those galaxies can have masses of 20 billion times the mass of our sun. In fact, I seem to recall that there is preliminary evidence of a black hole with something like 38 billion solar masses at the center of one of these cluster center galaxies. Small galaxies tend to have a lot more in the way of spiral galaxies than do the large clusters. Large clusters tend to have more big elliptical galaxies because they've undergone more mergers. So here is a really cool picture of a very nice galaxy cluster. And notice, so this I think is something like 2 billion light years away, and it's far enough away that much more distant galaxies that are in the background have their light bent enough along their traveling toward Earth that they get spread out by, this is what we call a gravitational lens. We discussed these when we talked about general relativity and black holes. And the result is that a lot of these galaxies are actually just multiple images of the same galaxy. And computers have become really, we have really good computer programs now that are able to work out which galaxies are the same, and if, say, a supernova explodes in one galaxy, how many months is it going to be when you see it in another image, that sort of thing. So there is a really large gravitational lens called J 0717.5 plus 3745. The picture is actually part of the background of this slide, but it actually contains at least 4 merging galaxy clusters. It makes for a really cool picture. This is one of my favorite pictures of the cosmos. You have 4 merging galaxy clusters or more, and you just have this giant gravitational lens. I mean, going back to the previous picture, here it looks like you're kind of looking down one of those tunnels, you know, one of those amusement park tunnels where you walk down a path in the dark and you have this star field or something that's rotating around in a cylinder. This kind of reminds you a little bit of that. But here, it's like it's rotating in different directions almost due to the effects of these different clusters resulting in different light travel paths among these different galaxy images and that sort of thing. It's just a really awesome picture here. Now, galaxy clusters can also be part of larger groups. We call these larger groups superclusters. And for a long time, we believed that the Virgo cluster was the central part of the Virgo supercluster, and it still is. And the local group was kind of on the outskirts of the Virgo supercluster, and still is, and that the Virgo supercluster was the largest gravitational entity of which we were a part. But we now realize that the Virgo supercluster is part of an even bigger supercluster that we call the Laniakea supercluster. So it's the Laniakea supercluster, I think, is something like 500 million light years wide, something like that. It's a really huge structure. But yeah, galaxy superclusters are the largest gravitationally associated objects in the universe. What's the difference between a cluster and a supercluster? Well, a cluster of galaxies, these things are all gravitationally bound together. Nothing's going to happen to them. I mean, yeah, they might merge together, that sort of thing, but they're not going to end up getting torn away or anything like that. But in the case of galaxy superclusters, the accelerating expansion of our universe is enough that eventually different clusters in a supercluster will end up getting pulled away from each other. So eventually, after a while, they're going to get pulled away so far that there's not going to be any chance of them ever becoming gravitationally bound. That's the difference between a cluster and a supercluster. And together, those things end up making up the cosmic web.